Okay, this is the simple harmonic motion lecture, and yeah, to get us started off, we need to first define what exactly is simple harmonic motion, and this is an important definition. It'll come up during a lot of multiple choice kind of questions. It can help you with those. Yeah, and what simple harmonic motion is, it's oscillation when the restoring force is directly proportional to the change in the x position, or the change in position from the equilibrium position. So this immediately tells us off that we're gonna have some sort of like spring or pendulum kind of thing that will require it to have a equilibrium position, right? Otherwise we can't have it change in position from equilibrium position. And yeah, that's what simple harmonic motion is. I think an example of this that we've worked with already is Hooke's law, which just states that the force of a spring is equal to the spring constant times the change in position from the equilibrium position, right? That's what delta x is. And yeah, this is obviously a restoring force, which is directly proportional to an equilibrium position, right? Because this is technically a negative k. This is a force that works against whichever way you change in your x-axis. You know, you just think of a spring. It goes back after you moved it. If I move a spring to the right, if I stretch it to the right, the restoring force is now going to act in the left. So it's restoring, because it's restoring it to equilibrium position. So yeah, this is why Hooke's law exists for ideal springs, or is always applicable to ideal springs, that is. And that's most of what there is to simple harmonic motion, right? It's just change in position from an equilibrium position. There's no trick to it. It's just that simple. So now that we have that, we need to work out a few equations for simple harmonic motion. And to get us started, let's just think of a spring. Right, we have a little springy boy right here. And this spring would theoretically be moving all over the place, right? We can say that this middle one right over here is the equilibrium position. And we can say that this is a distance equal to the amplitude, which is the max distance from its equilibrium position, max x. So this is amplitude. Oh, I already wrote that down. Sorry. And this right here would be negative amplitude, right? Just max x, but in the other direction. So yeah, when you look at this, you obviously think you have the spring here, and then it starts moving, it's going, woo, and then it comes right back up after hitting a max value, and then comes back after hitting a small value. And what does that make you think of? Well, I don't know about anyone else, but that makes me think of a circle, right? A circle has a distance, radius r, which is amplitude. You can think of this x side here, over here, as the amplitude. And if you just think in terms of x, now it's at the max amplitude it has, and it's going to go back up and up and up until it reaches another equilibrium position where it's now down. Now it's going to go down into negative until now it's negative x, the same amplitude or absolute value of that amplitude, just in the opposite direction. And now it's obviously getting bigger until it's 0 again. And then it does the same thing again where it gets bigger and bigger and bigger until it's the max amplitude, and it repeats onward like this forever, which is what a spring will do if it's in simple harmonic motion and obviously has no frictional forces acting upon it. So instead of just having a circle like this, we can kind of stop to think of the circle as a sort of Well, we can imagine that this thing right here is actually a string, and on the string we have a ball that's in motion. At this point of the circle, this ball has maximum speed, and it's going to travel along right here until it reaches this point, at which point all its speed, all its kinetic energy has turned into gravitational energy. So now it's not moving, but the gravity of this ball is now going to make it start tilting forward until again it's at max speed. And now again it's going to keep going, speeding up. And then over here, well, technically, we could kind of just ignore this bottom half of the circle because this is where the analogy falls apart. So we could just think of it as a semicircle instead. But you get the point. Now imagine that instead of going down, this ball now comes back up with the same speed that it would have down here. Like it just bounced off of this floor here, like a super bouncy ball that would never lose any frictional energies. And it does the same thing, up and down, up and down. And the reason it's useful to view it in this manner is because now you can imagine that if we have an angle theta right here, at any given moment, we could tell what this x component of the ball's position is, i.e. its distance from the equilibrium position, simply with cosine of theta, right, times the radius, or which is also the amplitude of the spring. And this would give us its x position. Yeah. Now, when we stop to think about it, what this theta would really be, since we're imagining this as a ball just moving along like this in with rotational velocity, this angle theta would just be equal to its rotational velocity times time, right? Because that's what theta is, right? We know that theta, or at least rotational velocity, is equal to theta over radius. That actually doesn't matter. Sorry, that theta is equal to rotational velocity over t. And yeah, so at any given moment, if we check what its rotational velocity is at this moment in time right here, we just pause it and we look at that. Then we multiply it by the time it took for it to get to that moment from this initial moment, or just since whenever you started the motion in general, because it's a cosine, right? It's going to change back up, so it doesn't matter. Then that's going to be your angle theta. So this really gives us the idea that the position x. So this gives us the idea that its x position is essentially going to be equal to cosine times whatever the rotational velocity would be times t times the amplitude of a spring, right? Because that's just how we derive this. And obviously we can rewrite this rotational velocity as simply the translational velocity of the spring over its radius or amplitude. So this is not just like a random kind of weird thing that we have there that doesn't actually pertain to the spring. And yeah, so this equation is obviously helpful because we can now find the velocity equation for a spring at any given time and the acceleration simply by deriving the terms here. What was I saying? Right, yeah, so derivations. I remember how to do that. Yeah, derivations. So essentially t is our changing function here. Excuse me. Oh yeah, t is our x variable, and x is going to be our y, for lack of a better term, because these two are going to remain constant. So our velocity at any given moment, that's why it's constant, because at any given moment. That's why w would be constant. Our velocity is then equal to, we simply use the, why did I forget what it's called? Chain rule, the chain rule, by deriving this inside part, and we know that it's going to be equal to rotational velocity times, and we can move this a forward here if we want to. And then again, chain rule, we're still doing the chain rule, so the derivative of cosine is negative sine. Wait, no. Yeah, is it? Am I dumb? I could be dumb. Cosine to sine. Hang on, wait. No, question, oh god, integrals have made me question stuff. So yeah, and we know that the Jesus Christ. Yeah, so we know that the derivative of cosine is just negative sine. And now this remains inside because that's how the chain rule goes. And that's the velocity of our function now, or the velocity of, I can think of a spring at any given moment. And we can even go ahead and derive the acceleration as well if we want to. Right, again, chain rule, so now it's w squared. Right, that's cool. So you just take this negative a, or negative wa still, right, and then chain rule of sine of w times t, so now this w squared. Now you multiply this by simply cosine of this inner part, chain rule, yay fun, and that's our acceleration. And yeah, these are just three kind of simple, you only need to memorize one of them, and then the rest are easily derived. Rules for motion, for spring, I don't know, motion, I guess, is fine in position of spring. Yeah. Now, alternatively, we know that a full period for this spring, okay, no, first of all, we know that this will have the greatest velocity at this point, right? Because now it has velocity that goes to gravitational energy, right? And this point as well, I guess, if you want to say, but we're just going to focus on this point, right? And it has the greatest velocity here is essentially what we're getting at, because you initially displace it this way, or you could displace it this way. It doesn't matter, just wherever you initially displace it into, and assuming you set your positive direction in that direction, that's when it's going to have its highest. I suppose the direction doesn't matter much, does it? So I'm just going to put it as simply whenever it's displaced the most, whenever the x, so here or here, is when the velocity is going to be highest. And yeah, this alternatively means that since one full period it starts here, goes here, so now it's down here, and it comes back here, we know that the how do I say this? If we try and take directions into account, then we can bring this bottom half of the circle back into play, at which point now the velocity here is actually the lowest as it's accelerating down, right? So, and this is one full period, which is just, right, to go from here to here, which is 2 pi, or 2 pi over theta. It's, my brain functions, I promise you. A period is what? Oh, a period is just 2 pi. Wait. Yeah. Yeah? Yeah. No, maybe. I don't know. Yeah, we know that period is just 2 pi over rotational velocity, right? This is one of our equations from previous units. And in this context, which it can change this, the period is equal to 2 pi over, this is just our omega is equal to velocity over radius, and our radius is equal to amplitude. So 2 pi times amplitude over velocity. Which likewise means that our velocity at any max time, that's a really bad V, isn't it? Our velocity at any max time is going to be equal to 2 pi times amplitude over period. Which I'd say is pretty cool. And, yeah. When we look back at a spring, and we think about it in terms of energy now, we know that this is quite simple energy-wise. You just have kinetic energy at this point, which just gets transferred over to potential energy, potential spring energy at this point, which then gets transferred to kinetic, kinetic to potential, potential to kinetic, kinetic to potential, and so on and so forth. So what this really tells us is that the maximum potential energy of the spring would be equal to the maximum kinetic energy of the spring. Yeah. And we can simply rewrite this as 1/2 times k times delta x max is just amplitude. That's its definition. So times a squared is equal to 1/2 times the mass times the velocity max of the spring squared. This over here is max, if you remember. Yeah. That's cool. Why is that cool? Because we can now simplify this equation, take these out, and we have k a squared is equal to, what is this? That's an m. That's a really bad m. To m by, and now we plug in this big guy. So by 4 pi squared times amplitude squared over t squared. And these two will obviously cancel out now. And you will be left with numbers which are numbers. What am I saying? I don't know. Yeah, we want to isolate t here. So we have another equation for t, because period is going to be big for us to find. So we multiply both sides by t squared, then divides both sides by k, and we have t squared is equal to 4 pi squared times m over k. And now we can just square root both sides, and we end up with t is equal to 2 pi by the root of m over k for spring. And this is a very important equation. It comes up a lot. You really can just memorize this. It's pretty simple. Just remember, t is equal to 2 pi by the root of k. I doubt it, but k, man. Get it? Because it's mk. So it's like an k sound. And there we go. That's how you memorize the equation. Right there. Bada bing, bada boom. And yeah, it genuinely is really useful. It's coming up on a lot of tests. And yeah. Beyond that. What is beyond that? I think that's most of it for spring simple harmonic motion. But luckily for us, there is more to this than just spring motion, because AP Physics 1 also wants you to cover pendulums, because that is also simple harmonic motion. So a pendulum is pretty nifty. I'd say that's a Discord message. Terrifying. Pretty nifty, pretty nifty. Why did I say pretty nifty? I don't know. No one knows. These are questionable times. Right? This is our pendulum, an angle theta. A little pendulum dude. And it's just going to go through the motions. This is going to be equal to angle theta. Or at least, you know, yeah. My throat is dead. I apologize. So, we know that a pendulum would only really be in simple harmonic motion, though, if it's released at like this angle theta is pretty small. Because I mean, come to think of it, like you have a ball hanging from a string, right, and you drop it from like up here. I think most can kind of intuitively sense that it's gonna get really weird. The tension of the string is gonna get messed up and all that kind of sort of stuff. And it's not really going to be in any sort of simple harmonic motion. It's just going to be really weird and like jerky in its movement. So that's just something to keep in mind as we move along here with these derivations. Yeah. Now, when we look at this, we just learned about torque and all that stuff. So we immediately can think that for this pendulum right here, the torque acting upon it, or for this ball of mass, the torque acting upon it is just going to be equal to the perpendicular gravitational force multiplied by the string length, which we'll call lamed, times lamed. You can literally call it anything you want. You can call it L, you can call it big L, you could call it string length and just write that out. You can call it S, it doesn't matter. I'm just using lamed because I think it kind of gives me the vibe of string length. I don't know how to explain it. Yeah. So that's cool. And we can rewrite this equation, right, as simply tau is equal to mass times gravitational force times sine of theta times the string length. And we can even go ahead and set this equal to I alpha, because it's tau, right? Tau is always going to be equal to I net alpha net. And there's multiple things that can happen now that we have this general equation. The first thing is that, remember how we discussed how this angle theta has to be really small? That means that, if you remember from last time when we had when we were deriving y, we used theta, not like tangent of theta or anything, for the, what do you call it? I can remember, I promise. It's on the tip of my tongue. Jesus, I don't remember. Wait, for the torque lecture, when we're deriving torque. Since this theta is going to be really small, we can quite literally just cut out the sign and just say that it's m times g times the angle theta times lamed. That is now going to be equal to I alpha. And now this I alpha we can also simplify. You know that I is just mass times radius squared. Our radius is lamed now, so it's mass times lamed squared. Then alpha is a over radius. Radius is lamed, right? And then we can cancel these out. And it's really just mg theta lamed is equal to m lamed alpha. And we can now go ahead and cancel these terms since they repeat in both. And we end up with g times theta is going to be equal to our acceleration for a pendulum, which is a really nice and simple kind of equation for this, I think. Just 3 variables. That's all you need. It's really easy to work with. It's really fun. It's cool. We can take this a step further now and simplify it, or making it useful for us, by saying that g times, and now we take theta and split it into x over radius, because that's what theta is, and the radius is lamed, and that is equal to our acceleration. And yeah, what is going on there? Oh, yeah. So, now that we're at this point, if you remember these equations that we derived back here, we're going to look for this one and this one. These would obviously also be applicable in this situation, because we derive these out of this sort of circle that explains to us, is just a different way of showing us what this motion is. So this is going to hold even in this situation down here, because this theta is obviously going to be limited by this, so we won't have to worry about all these weird issues that would crop up if it went to like theta equals, I don't know, 6 pi. Wait, 8 pi. Wait, yeah, 8 pi would work. 6 pi also works. I digress. Yeah, so since this could also, these equations can be plugged in here, that's just what we're going to do, which means that this simple equation is going to look a bit scary, but it's completely workable, you'll see. And we end up with g over lamed is equal to, and now our x equation, so let me flip back to where I have it. Our x equation was equal to amplitude, times amplitude, right, times cosine of rotational velocity times our time t. And we have this is equal to our acceleration, and our acceleration equation was simply negative rotational velocity squared times amplitude times cosine, was it again? Yeah, cosine of rotational velocity times time t. And we could go ahead and cancel these out immediately right off the bat, just looking at them. And that's fun. So we have this done, and it's probably notable to mention that we are trying to make this into another period equation. As I mentioned, period equations tend to be really useful in this unit. So how would we go about getting period in here? Can anyone think? I don't know why I'm phrasing that as a question. I'm alone here. Yeah, that's right. We just take our... Oh, I digress. We can also cancel out cosines, because these are the same thing. So yeah, we can get period here using this equation. Period is equal to 2 pi over w. So since period equals 2 pi over w, then we know that w is going to be equal to 2 pi over period, so w squared equals 4 pi squared over period squared. And now we just shove this in. So we have g over lamed is going to be equal to negative 4 pi squared over t squared. Right, then we just switch around our variables. We multiply both sides by t squared, multiply both sides by lamed, divide both sides by g, and we end up with t squared is equal to negative 4 pi squared times lamed over g. And then we could even go ahead and just square root both sides, right? And then we end up with t is equal to negative 2 pi. This negative will obviously not really matter. We don't really care much for the negative stuff. This is time, so it can't actually be negative. So we could even just go ahead and forget that negative. So 2 pi times the root of lamed over g. And yeah, that's most of this. That's that. This is our cool equation, fun times for pendulum. Aside from this, I think the only other important aspect that I can think of right now that pertains to pendulums and springs in this motion is energy graphs and force graphs, obviously. And those are pretty simple. If you just have some made up graph here, and we just say this is max energy, and we say that this here is, I don't know, negative. I guess we just make that the 0 position A, that would be easier. So this would be negative amplitude, and we can think of this amplitude as either that of when the theta, or we can think of amplitude as when theta is highest, obviously. And it could be either pendulum or spring, it doesn't really matter. So yeah, negative amplitude, equilibrium, so EQ position, and amplitude. So this is x-axis, representing x. This is energy, y-axis is our energy, and this is energy max, as I've explained. And if we just go ahead and give it a quick think here, we know that our kinetic energy is going to be highest when the system is in the equilibrium position, right? Because just think of a spring moving. Or actually, we don't even need to think of a spring moving, I guess. It doesn't really matter. Kinetic energy is 1/2 times mass times v squared. In both cases, spring and pendulum, the mass is going to be the same. And in both cases, the velocity can be found using this here equation. And if we simplify this into theta, we know that the velocity will be equal to its highest value when it's at its equilibrium position, its starting position, which is when this is equal to 1. Oh, sorry, this is the equilibrium position, which is not the starting position. I don't know why I said starting position. When this here is equal to 1, which is obviously, sine is this is cosine, radian wheel stuff. So that's why velocity is highest whenever it's in the equilibrium position for both of them. So we just go ahead and say that this is what the graph looks like, because it's a cosine graph, so right, just a little cosine wave function. That's what it's going to look like in this portion. And this is our kinetic energy. And our potential energy is going to be this thing's exact opposite. If this is a cosine graph, then potential energy will be a sine graph. Because potential energy is going to be, for the spring, it's going to be 1/2 times this k, and these are both going to be constant, times delta x squared. So obviously when it's at the furthest x at its amplitude, this is going to be at its max. I think that's pretty intuitive for most of us to guess. And it's a bit harder to see with equations with our pendulum, but essentially just have UG is equal to MGH. I guess it's still harder to see with the equations. And obviously it's going to have the highest height when it's the furthest distance it can be from its equilibrium position, so up here, because that's its max height. And obviously these will be constants. So that's what the peaks for the potential energy would be for either one of these, either potential spring or potential gravitational. It doesn't matter, it just depends on which system you're looking at. And again, x would be given to us. We're using x because this is age and this is obviously just x. Would be given to us with cosine graphs. It's just the opposite of a sine graph. So if we just graph a little cosine wave to go through these, where this is a sine wave, we get a little parabola looking guy. Not a genuine parabola, mind you. It's important distinction. It's a cosine graph, not a parabola, like half of a cosine wave. But it looks like one. And this is UG. And yeah, that's basically it. From here on out, you can pretty much intuitively sense what any other graphs relating to all this would be if it's set by x. You can have a force graph by x, right? And if you just think of a spring, because we know it's going to be the same for a spring and a pendulum, they look the same in these graphs, courtesy of our equations over here. So for a spring, if you stop to think about it, the highest spring force would be when it's the greatest distance from its equilibrium position. So again, you have EQ, right? You have amplitude, you have negative amplitude. Force is highest at these points. It's still a cosine graph and whatnot, because MA, right? And A we know is cosine. Jesus Christ, there's a person outside my window. So yeah. Scared me, that was my brother. I digress. Yeah, it's gonna be a cosine graph with this force here. We could stop the thing, instead of force we now have a velocity graph. I hope I don't need to mention why the velocity graph would look the same as the kinetic energy graph. It's because of this, and these are constant, so it's gonna look more or less the same. Or obviously you could just graph this function, I guess. That's also another way to look at it. You could have an acceleration graph, which will obviously again look the same as the force graph, just now this y-axis will be scaled down by the mass of the spring or pendulum, because force is ma. And yeah, that's all that. It's all of that. Yeah, that's it. Bye.